Alright, so just as a review of where we're at here, again, remember, if we have a complete neutral solution, then we have the exact same amount of hydronium and hydroxide concentrations. And it ends up being 10 to the negative 7 molar, which reflects a pH of 7. And you can see in this lovely picture that we have a complete equal balance between hydronium and hydroxide. If we put in an acid into water, then the amount of hydroniums goes way up without the hydroxide concentration going with it. So the concentration of hydronium is way greater. The further away from neutral you get, the further away from a pH of 7, then you see a stronger acid, like battery acid, a very, very strong acid. You really don't want to get that on your skin, in your mouth, etc. But juices and coffee have a pH less than 7. They are acidic, but they're not going to do any major damage to us as far as harm is concerned. Bases, the hydroxide goes way up, and the hydronium does not. So the concentration of hydroxide in a basic solution is way greater than hydronium. And again, same thing, way over here, drain cleaner, again, something you don't want to mess with chemically, but antacids when your tummy hurts, baking soda that you put into different recipes, those aren't going to do much damage to us. So that's a little refresher of where you are. You see on this pH scale a bunch of different colors. And that's a reflection because of these things called indicators. When we deal with acids and bases, there are these compounds that will change color depending on the pH of a solution. Some exist naturally, like there's actually some flowers that if you plant them, and if the soil is acidic, they'll be red flowers, pink, and if the soil is basic, they'll be purple flowers. And it's because they have these indicators present in them. And so you can see here range of different indicators. So for example, litmus. Litmus here, when it is in an acidic situation, then it'll be a pinkish reddish color. Once it's in a basic situation, then it'll be bluish purplish. Another one here, phenolphthalein. When it's in an acidic situation, it stays clear. When it's in a basic situation, it'll turn a bright pink magenta. And we're going to be working with these different indicators in the labs to try and figure out if we have an acid, a base, a weak acid, a weak base, or a neutral solution. Again, litmus typically comes in paper form, so you touch litmus paper to an acid or base and it'll turn bluish or reddish. This pH paper stuff we'll work with is pretty nice because you can see here that it gives you a whole different set of color changes based on the pH. So that can be quite helpful. Same with universal indicator, it has a pretty nice range. We're going to be using that when we do acid-base titrations, trying to get a greenish color signifying the end of our titration. Here's a peek at that phenolphthalein stuff I was talking about. If it goes into an acid, it stays clear. If it goes into a base, you see the pinkish magenta color. If you decide to continue on studying this lovely subject, perhaps when you get to college you'll encounter some pH meters, which, this probe goes into the solution and it digitally tells you exactly what the pH of that solution is. So, of course, our buddy Don Showalter, his lab, of course, has a pH meter. But not as much fun as playing mixy-mixy with the indicators and seeing all the different colors, which is what we'll be doing in lab for the first time. Alright. Last section here for this video. What we've been talking about so far is considered what's known as the Arrhenius theory of acids and bases, the very fundamentals. If you look at all our acid and base formulas that we typically use, all of the acid formulas have hydrogens in them. So when you put those into water, a water molecule and the hydrogens from the acid come together and make a hydronium. Acids. If you look at our base compounds, sodium hydroxide, magnesium hydroxide, potassium hydroxide, they all have hydroxides in them. So when you put them into water and they dissolve, they dissociate, that's where the hydroxides come from. Well, one of them that sticks out, if you look at our list of acids and bases, is ammonia. Ammonia is NH3. It is definitely a base. It's probably one of the more common bases you'll encounter in your lifetimes. Looking at that formula, though, you'd think it's an acid because it only has hydrogen in it. Well, that's what some people started studying, like Bronsted-Lowry here, and redefined acids and bases a little bit. These acid-base reactions are viewed through hydrogen transfer. A acid is a hydrogen ion donor. It will give a hydrogen to a base, which is the hydrogen ion acceptor. So let's see this in action. And let's use ammonia, because that's what we're here to talk about. So here we see when we put ammonia into water, aha, there's our buddy hydroxide to show that it is indeed a base. So, because what's happening is when ammonia goes into water, the water is giving up a hydrogen to the ammonia. So it goes from being ammonia to ammonium, which is NH4 plus 1. You see our little double arrows, that's one of our dynamic equilibriums. So just as easily as ammonia and water can react, ammonium can bump into hydroxide and give a hydrogen back. So a hydrogen can transfer that way, and you can go back to being ammonia and water. Looking at our definitions, acids donate, bases accept. So the acid donates a hydrogen to the base. Same thing over here. The acid donates a hydrogen to the base. Except on this side, we call them the conjugates. So if we're talking chemistry E's and someone says the conjugate acid, I know, oh, okay, that's on the product side. Take 10 seconds and see if you can label this equation the same way we labeled that one. Pause the video, of course, don't cheat. Alright, so hopefully you saw that, well, this is hydrochloric acid. It gives a hydrogen to water, and that's where we see our good buddy hydronium. On the other side, this is the only way hydrogen can go, since chloride doesn't even have a hydrogen. And so again, hydrochloric acid giving a hydrogen to the base. Same thing on this side, the conjugate acid gives to the conjugate base. So what is goofy about that? Well, look. Here I tell you that water's an acid. Here I tell you that water's a base. And before I've told you that water is neutral. What the heck? Just add this to the list of incredibly awesome things about water. Water is what we call amphoteric. Alright, so definitely true, when water is by itself, it is a neutral substance. Two water molecules collide, you get a hydronium and hydroxide. But when you put substances into water, it can donate a hydrogen and become a hydroxide, or it can accept a hydrogen and become hydronium. So it has the ability to act as both an acid and a base, amphoteric. And of course Kermit is here. He's an amphibian on both land and water. If you get a chance, take a course in Latin. You can find out a lot about words. Amphibian, land and water. Amphoteric can be an acid and a base. So that's this section of notes, and perhaps I'll see you on the next one.